Let's take a look at our second type of intermolecular force, and these are known as dipole-dipole interactions. And these are attractions between permanent dipoles. That's what sets this apart from London dispersion forces, is that these are molecules that have a permanent dipole in them. And so that means these have to be polar molecules. So there's that term polar again. Again, I'm comparing polar to non-polar. You really need to be able to recognize if a compound is polar or not. And so let's take a look at a molecule of formaldehyde. So here's the Lewis structure. And that carbon-oxygen bond is a polar bond. There's a difference in electronegativity of the oxygen and the carbon. And so there's this dipole that goes in the direction of the oxygen. Now let's associate this with another molecule of formaldehyde, which has the exact same dipole moment. The oxygen's partially negative, the carbon is partially positive. Where do you think the attraction is going to lie? The attraction is going to be between this negative pole of oxygen and this positive pole of carbon. And so this is why they call this a dipole-dipole interaction. Now, these are much stronger than London dispersion forces because they're based off of something that is permanent. It's not fleeting or temporary. These are permanent intermolecular forces. And so something that is polar, so a compound that is polar has a much higher boiling point than something that is nonpolar. And I want to put a caveat to this, as long as you're comparing compounds with similar molar masses. And again, I highlight that because if we look back at our previous video here, all right, octane here is polar, I'm sorry, non-polar, and methanol is polar, yet there's a huge difference in their boiling points. And so the main reason for that is we're not comparing two molecules with a similar molecular weight. Now, just to review, you have to consider the shape of a molecule, because if we look at something like, say, carbon dioxide, even though carbon dioxide has polar bonds in it, it's a non-polar molecule. Now, with a molar mass of 44 grams per mole, its boiling point is negative 78 degrees Celsius. The only intermolecular forces it has are London dispersion forces. And if we compare that to formaldehyde, which we've already highlighted is a polar molecule, it has London dispersion forces as well as dipole-dipole interactions. Its boiling point is about 70 degrees higher, even though its molar mass is a little less than carbon dioxide. All right, so that's a quick summary of dipole-dipole interactions. In our next video, we're going to kind of wrap this up and look at our last intermolecular force.